All right, so for this chapter, this is a review of most of most of this, I should say, is a review of something we did in intro chem. So we're going to be looking at the electron structure outside the nucleus, which means electron configurations, orbital diagrams, valence electrons versus core electrons. And then the next chapter will be the bonding, where we do Lewis structures and look at, how many bonds are in carbon dioxide, things like that. So this first module, this is a module that I think students usually do really well with. It, as long as you remember like the little glitches on the periodic table, most students are really good with this. So I've got my periodic table out here. If you go into my courses, there's a color-coded table for you as well, and you could just print that out or look at that later. And I think most of you are going to remember this anyway from intro. But essentially, for the purposes of electron configurations, I really like helium over here above beryllium. And the reason for that, and I'm just going to kind of cross it out over here, is because when we look at electron structure, helium really belongs with the alkaline earth metals, but it's a noble gas, so it's fair. It's over with the noble gas family. So hydrogen and helium are two that, different periodic tables will put them in different spots. Okay, so the main focus of this chapter is we're looking at the electron structure. And we seem to have a pretty good idea of what that structure is. And this is all done by mathematical probability, which always just I thought was fascinating. So the first thing is that we know the electrons are outside the nucleus. We always start there. But we have to kind of go with this idea that number one, an electron next to an electron makes the electron unhappy because two negative particles will repel against each other. So an electron really doesn't want to have to sit right next to another electron. So they're certainly not going to all be huddled together. But the electron really does want to be close to the nucleus because the positives and negatives, right? That's an attractive force. And the closer the electron can get to the nucleus, the happier it will be. So the first sort of level of organization, I would say, is if I just sort of look at my nucleus, I'll just put N for nucleus. We have energy levels or energy shells. And I use both terms. Unfortunately, I use them kind of interchangeably because in my mind they're the same. And I've heard both terms. So energy level or energy shell. And when we were doing our quantum numbers back in chapter 8, this was our N. And we saw that N could be any whole number, 1, 2, 3. Basically, we just can keep on going. If we look at the periodic table, that principal quantum number or N, it corresponds kind of, we'll explain the kind of part here in a little bit, but to the row on the periodic table. So when I look at my periodic table, as of right now, we only have 7, right? So what this is saying is hydrogen and helium have their electrons in the first energy shell. So that means here's my nucleus. They don't have a lot of electrons because they're small, obviously, right? Hydrogen only 1, helium 2. And those 2 electrons can fit in that first shell. And then that's it. When we go to lithium, we're now in row 2. So we've had to now start to fill the second shell. And all of the elements that are in row 2, which is lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon, they have all of their electrons in the first 2 shells. So the first shell is always filled first because, again, that's the best seat in the house for the electron. And then from lithium to neon, we now start to fill that second shell. And then at neon, right, we filled the shell because after neon, we go to row 3, which is sodium, and that begins filling the third shell. So that's the principal quantum number, which we learned in chapter 8. And it's a shell of 1, 2, 3, 4, et cetera. And however many shells are occupied depends on the size of the atom. And you can get that quickly from the table, right? If I'm looking at strontium, strontium has 5 occupied shells, 5th being the highest. Chromium only has 4 occupied shells, 4 being the highest, right? If I have something like osmium, now I've got 6 occupied shells. So that part's pretty straightforward. That's the first way we organize the electrons. So we can put some electrons in the first shell, right, orbiting the nucleus. Then we can put some in the second shell, then some in the third shell, et cetera. And we always build out. So you always fill the closest energy shells first, and then you go to the next, and then you go to the next. So that's the first thing. Then within that energy shell, all right, so this is like the first level of organization. So energy shell, and as I mentioned, also called energy level. I see both. Within that, so we're kind of narrowing it down a little bit smaller. So the first sort of broad umbrella is the energy level or the energy shell. within that energy shell or energy level, you can have a subshell or a sublevel. All right, so again, both terms, and again, I kind of use them both without thinking about it because in my mind, they're exactly the same. So this is where we were looking at our L back in chapter 8, and we had values of 0, 1, 2, and 3. Theoretically, there are more values than that, but those are the only ones that we have on the periodic table. And this is the S, P, D, and F blocks on the periodic table. So within an energy shell, we can narrow it down even more and look at electrons in specific regions of space. If it is an S subshell, if we remember, S is a sphere, right? Easy to remember. So there's the nucleus in the center. That spherical shape is really nice. Energetically, that's the best one because it matches the shape of the nucleus. So that makes sense. The electron can just orbit that nucleus, and that's a nice spatial arrangement since it matches the shape of the nucleus. Then when we look at P, if you remember these from intro or from the last chapter, the P subshell is where we put electrons specifically on an axis. And so what we can sort of say here is that we're going to put electrons going side to side on the x-axis, electrons up and down on the y-axis, and then electrons out and back on the z-axis. And all of that combined is the P sublevel. Then it makes sense that if you have electrons confined to the axes, the d orbitals come along and they go between the axes. So they'll have names like dxy, dyz. So now we're going in between the axes, and etc. So the organization of the electrons is, number one, they go into these shells right around the nucleus. Within the shell, we can have different specific regions in space. First, spherical orbit. Second, let's put electrons just on the axes. Third, we can come in and put between the axes if we need to. So that is how this is all organized. And like we were talking about, N matches up kind of, right? Again, kind of. There's always an asterisk with chemistry. N is that row on the periodic table. The L is the block on the periodic table. So when I look at my periodic table, the hydrogen, helium, and then the alkali and alkaline earth metals, those two columns on the left correspond to an S sublevel or an S subshell. That's the sphere. Then if we look at our transition metals, right, in here, this is our D sublevel or subshell. So just those 10 columns right there in the middle. So from scandium to zinc, right? And then over on the right side, from boron to neon, these 6 taller columns on the right. This is our P sublevel or subshell. And then down at the bottom, our lanthanide and actinide series, this corresponds to our F sublevel or SF subshell. So again, going back to chapter 8, S, remember, was an L of 0. P was an L of 1. D is an L of 2, and F was an L of 3. So kind of bringing back those quantum numbers. Remember last chapter, I was like, I never understand why textbooks break this up into 2 chapters, but they do. But anyway, so it is what it is. Now, the third type we can organize these electrons or sort of look at where they are specifically in space is within that subshell or sublevel, we have a specific orbital. And an orbital has a rule. We can have a max of 2 electrons per orbital. So I always like using the P subshell because it's nice and easy to visualize, I think, to sort of look at these orbital spaces on the axes. Altogether, the P subshell includes the X, the Y, and the Z. But if I look at a specific orbital, I'm just going to look at one dimension. So I can fit 2 electrons going side to side. I could fit another 2 going up and down, and then another 2 out and back. Altogether, 2, 4, 6 can fit in the P subshell, but in a P orbital, you can only fit 2 electrons. So you have to be careful about this because the practice quiz, you just have to know your terminology. So if I look at the P block, right, this P subshell or sublevel, the P subshell fits, 6 electrons. And if I forget that, all I have to do is count over, right? Because every increase in space, right, in the periodic table, I'm adding a proton, I'm adding an electron, right? So basically every space is an electron added to the atomic structure. So I have room for 1, 2, 3, 4, 5, 6 electrons in the subshell or sublevel. But an orbital, by definition, fits only 2 electrons. So that is a rule for electron configurations and orbital diagrams, is that any one specific region in space, the orbital, can only fit 2 electrons. So what we understand here is that if the subshell can fit 6 electrons, but it's only 2 electrons per orbital, that means that there must be 3 different p orbitals. And we looked at that. That was the px, the py, and the pz. All right, and so that's what we drew here. So those are the rules for the p subshell. If I go back to the s, right, the s subshell, there's only 2 columns there. So the subshell fits 2 electrons, but we also know that an orbital always fits 2 electrons. So that must mean that there's only 1 orbital. And so if you remember what we did in chapter 8, we said that when we were looking at S, we had an L of equal to 0, and that M sub L value was anything from negative L to positive L, which means it could only be 0. So there was just 1 orbital, right? And that is that spherical orbital. With P, we said that L was equal to 1, which meant that M sub L could be -1, 0, or +1. So there's 3 different p orbitals, the px, the py, the pz. So this is matching what we learned in the last chapter. Now with D, if we look at it, if we count all the way across, right, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, the subshell fits 10 electrons. If it's 2 electrons per orbital, that must mean that there's 5 different d orbitals. All right, and we said there was an L of 2, right? And when we learned our quantum numbers, the M sub L meant it could be -2, -1, 0, 1, or +2. There are 5 different values there because there's 5 different orbitals. So each one of those M sub L values corresponds to a specific orbital, right? -2, -1, 0, 1, 2, there's 5 different orbitals. With P, -1, 0, 1, there's 3 different p orbitals. All right, and then down at the bottom, if we look at F, again, we can just count over, but we've got 14 spots here. So the entire subshell or sublevel fits 14 electrons. And again, we don't have to memorize that. The table will tell us. And so that must mean that there are 7 different F orbitals. And if your L value is 3, that means your M sub L could be -3, -2, -1, 0, 1, 2, and 3. So there's 7 different M sub L values when you have an L of 3. All right, sorry, it froze, so I had to cancel it and then go back in. Okay, so in terms of our organization, right, with the electrons, the first is what shell do we put these electrons in? Always go to the first shell first and then build out. In those shells, what type of spatial arrangement are we looking at? And basically, when we do an electron configuration, the way my brain thought about it was I'm giving an address to all of the electrons. So I always like to start with the simplest, right? We got hydrogen, right? And so hydrogen, we know with atomic number 1, it only has 1 electron for us to worry about. So where does that 1 electron go? So what we talked about was we always fill that first energy level first, right? So it's going to go into energy level 1. So that's the N, the principal quantum number. It's in the S space, the S region, right? Because that's where we are on the periodic table. So there's my subshell. And then it has 1 electron in it. So that superscript, right, is the number of electrons. So hydrogen has a 1s1 electron configuration. If I look at helium right next to it, now with 2 electrons, it's still in row 1. It's still in the S space, but now there's 2 electrons in it. So 1s2. Now, not sulfur. The S subshell maxes out at 2 electrons, right? We only have 2 columns there. So we can't ever have like an S3 or an S4. That's as far as we go. Now, if I go in order of atomic number, right, the next element I would have is lithium. And so if I look at lithium always, every element starts 1s2. We start there, except hydrogen, which is 1s1. So we always fill that first. And then when we get to lithium, we have 2s first spot. So 2s1 to get to lithium. If I add up my superscripts here, 2 + 1, I've got 3. And that's the atomic for lithium. All right, so basically your order of filling matches the periodic table. So on our periodic table, we fill the 1s first, fills at 2, 1s2. 2s2. Then over here, we would get to 2p fills at 6, then 3s2. Then with aluminum, this is still row 3, so 3p fills at 6. Then we get our 4s2. And then with scandium, with the D block, we get to our first glitch. So remember earlier when I said kinda. All right, so scandium, the transition metals, what happens with D is we actually want to take the row number -1. So even though this is row 4, potassium, calcium, 4s, right? Scandium would start the 3D subshell. And the reason for that is even though it's in a closer energy shell, the third shell, rather than the fourth shell, like potassium and calcium, the spatial arrangement of the D orbitals is just not as nice as that spherical orbit, right? Remember the spherical orbit of the S matches the shape of the nucleus. So it actually turns out that for potassium and calcium, even though those electrons are farther away in a higher shell, the spatial arrangement of the S is better than going to shell 3 and filling in the D orbitals. So it's our first glitch on the periodic table. So the filling is 4s fills at 2, 3d fills at 10, go back to normal counting, 4p fills at 6, 5s fills at 2, yttrium would start the 4d shell or subshell. There's my 4d, cadmium is the end of that, 4d10. Then indium, go back to normal, 5p fills at 6, and then we get our 6s2. And then what you notice here between barium and lutetium, we have a little gap in atomic number. We went from 56 to 71. Those elements are down here at the bottom. That's your lanthanide series. And for the F, we want to take row -2, right? Because these are energetically really not very nice. So you'd have cesium and barium start the 6s. After that's filled, we go, I'm on periodic table, or my computer didn't want to go anywhere. Hold on. So after the 6s, then that gap, we go down here, lanthanum, right? This is row 6, where these elements would fit in right here. Row 6, but lanthanum starts the 4f subshell. So there's my 4f. All right, and then back to lutetium. Now remember row -1, so this would begin my 5d. All right, and then mercury would finish out the 5d10. Thallium back to normal, 6p. Radon goes to 6p6. And then francium starts the 7s, right? And then again, my next gap in atomic number between radium and lawrencium, that's my actinide series. That's down here. So row 7, actinium starts the 5f. All right, and that would fill at 14. And then lawrencium, going back where we left off, that is row 7, but it would be the 6d. All right, and again, it froze again. So I'm just canceling it out and going back in. So lawrencium, this would be my 6d. So when I was learning electron configurations, this is the way that it was taught to me. That was like, okay, in your first energy level with an N of 1, you only have one value for L, which is 0. You have a 1s. That's it. When you get to your second shell, right, N of 2, now you can have an L of 0 and an L of 1. All right, so 2s and 2p. When you get to your third shell, N of 3, you can have an L value of 0, 1, 2. So you can have a 3s, a 3p, and a 3d. When you get to the fourth shell, you can have an N of 4, which means an L of 0, 1, 2, 3. So 4s, 4p, 4d, and then 4f. All right, and then past that, if we kept going, 5s, 5p, 5d, 5f. Technically, we could keep going here. I think G comes next if memory serves, but I haven't looked at that in a really long time. But we don't have any elements in there anyway, so we don't have to worry about it. Then 6s, 6p, 6d, and then 7s, 7p. And that's as far as our periodic table goes anyway. Then the order of filling is your 1s goes first, the 2s, then your 2p, 3s, then your 3p, 4s, then your 4p, sorry, 3d is supposed to be over here. They kind of got, hey, let me move it over here so it's a little bit closer. So 3d, 4p, 5s. Oh, that came out sloppy. So we'd have our 3s, 3p, right? 3p to 4s. Then we'd have our 3d, 4p, 5s. And then if we kept going, we'd have our 4d, 5p, 6s, and then our 4F, 5D, 6P, 7S. And I always, like, I remember drawing that when I was learning it. And then I thought, well, there's such a simpler way. If I just remember that when I get to D, I take rho minus 1. And then when I get to F, I take rho minus 2. The order of filling is just right there on the table, right? So go with the atomic number, like reading a book left to right. 1S fills at 2, 2S, then the 2P, 3S, 3P, 4S, 3D, 4P, right? And you just keep going until you get to whatever element you're looking at in terms of the electron structure. So if we wanted to pick an element, I'm going to start with something kind of small and simple. I'm going to do aluminum. All right, so with aluminum, we have 13 electrons that we have to worry about. All right, so starting with aluminum, let's do the electron configuration. Okay, so electron configuration, again, I think of it as assigning an address for all of the electrons. So aluminum, number 13, we've got 13 electrons to say this is where they live. Remember, the first 2 electrons always go 1s2, right? We always fill the first energy shell first. So every electron configuration starts there. Then, like reading a book, 1s2, 2s2, 2p fills at 6, then 3s2, and then aluminum would be the 3p1 because it's the first spot. So 1s2, 2s2, 2p6, 3s2, 3p1. And if I look 2, 4, 10, 12, 13, there's my 13 electrons for aluminum. All right, so this is what's called the complete configuration, SPDF notation. Everything is there. We can abbreviate this electron configuration. And when we do an abbreviated electron configuration, we find the noble gas core. And when I look at any element on the periodic table, the noble gas core is I go up 1 row and all the way to the end. So for aluminum, my core is neon. If I were looking at bromine, my core would be argon. If I were looking at 10, it would be krypton. So any element on the periodic table, doesn't matter where it is, like nickel, we'd still do argon. But you find your element, go up a row and all the way to the end, that's your noble gas core. So aluminum has a neon core. And basically what that helps me do is instead of writing 1s2, 2s2, 2p6, I just write neon. And then I pick up from neon. So after neon, I've got 3s2 and 3p1. All right, so 3s2, 3p1. So what we're going to talk about next is there's a difference between what are called core electrons and valence electrons. Next chapter, when we do bonding, the valence electrons are always going to be the focus because the valence electrons are what decide the bonding. You know, how many bonds do we take? Is it ionic or covalent? If it's ionic, are electrons gained or lost? How many, right? That's what we're going to segue into. So your noble gas core, once you have that noble gas electron structure, I think of it like a stability switch clicks on, right? And so these core electrons are unreactive. Like once you've gotten to that S2P6, those electrons are not going to react. You can make them, but it's really, really difficult. So those are your core electrons. Next chapter, we're going to be focusing on the valence electrons. All right, and the valence electrons, again, are what's going to decide what happens here. Now, the valence electrons, there's kind of 2 definitions here, unfortunately. If it's a representative element, meaning not a transition element, your valence electrons are these electrons that are in the highest N. So what we see here is we have an N of 1, N of 2, N of 3. So the valence shell here is everything in the 3rd shell. So I've got my 3s2 and my 3p1. So there's a total of 3 valence electrons there, 2 in an s orbit and then 1 in a p. Okay, so I've got 3 valence electrons for aluminum. Now the valence electrons is going to be something we're going to want to very quickly grab when we go to do Lewis structures in the next chapter. And what we can do is actually just use our table to get that. The hydrogen column and the alkali metals, they all have 1 valence electron. It's an S1 configuration. Helium and the alkaline earth metals all have 2 valence electrons, so it's an S2 configuration. The valence electrons with the transition elements is more complicated. We'll talk about that more in a minute. Then when we get to boron, we have an S2P1, just like aluminum. There were 3 valence electrons for that family. Carbon, S2P2, there's going to be 4 valence electrons. Nitrogen group family will be 5. Oxygen family will be 6. The halogens will be 7. And then that stability switch clicks on with an S2P6, which means the noble gases have the 8. 2 in the S plus another 6 in the P. So we have 8. And that'll be an octet rule that we talk about in the next chapter with Lewis structures. So this will be a quick way to grab the number of valence electrons. So how many valence electrons in silicon? 4. How many valence electrons in bromine? 7. All right, so that'll be something we'll talk more about in the next chapter. Now, the other thing we can do here, looking at the electrons, is look at something called an orbital diagram. And what we're going to do with the orbital diagram is use a box or a dash to represent an orbital. And then we use an arrow to represent an electron. And you can do a complete orbital diagram, or you can do an abbreviated orbital diagram, just like you did with the electron configurations. I typically like doing the abbreviated more, just because when we do orbital diagrams, a lot of times what we're looking at is sort of looking at how many unpaired electrons we have, how many bonding sites do we have. And with the core electrons, it's not important. Everything's paired, no bonding sites, they're not reactive. It's the valence that decide that anyway. So with the abbreviated orbital diagram for aluminum, we'd still have a neon core. And then how many boxes, how many dashes is what we have to talk about next. When we're talking about an S subshell, we said there was only one orbital. So we only draw one box. So when I'm drawing my 3s2, right, I'm going to draw my 3s, just one box. The 2 is the number of electrons, which means I need 2 electrons, so 2 arrows. So I'm going to put 2 arrows in this box. Now, the second rule of electron configurations and orbital diagrams is we talked about if electrons are forced to pair in the same orbital space, they don't really love that, right? Because they repel against each other. So one way to offset some of that repulsion is to give them opposite spins. So one arrow is up, one arrow is down. And again, that's to say that one of them is spinning in one direction and the other one is spinning in the other direction. And that helps offset the repulsion just a little bit. So my 3s2, I've got my box for my S space, 2 electrons in it. So 2 arrows, opposite spins, one up, one down. Now, when I go to do the P subshell, we said that for P, there should be 3 orbitals, right? And those orbitals, the PX, the PY, the PZ, they are what's called degenerate. All right, degenerate means that they are equal in energy, and all together they make up the 3p subshell. Now for aluminum, I don't need all 3 of them, but I have to draw them anyway because I have to show all possibilities for this 3p subshell. So the rules with filling a subshell are you start in the left box and you start arrow up. So that would be aluminum. That would be it, my 3s2, 3p1. If I went one more spot on the periodic table to silicon, I would now go into the second box, arrow up. That second electron has an option. Each one of those 3 orbitals is equal in energy. It's in terms of getting close to the nucleus and how much energy stabilization that is, they're all equal. The electron doesn't care if it's on the X, Y, or Z axis. So the electron comes in and says, okay, well, I can sit in this first orbital, but then lose some of my energy because of repulsion, or I can sit in my own seat. And the electron says, I'd much rather sit by myself. They're introverts, I guess. All right, so the second electron, if I had a P2, right, P2 would go into the second box, and then P3 would go into the third box. So let's take an example. Let's look at, let's do 10. All right, SN. And so for 10, we have 50 electrons. So rather than doing the complete, let's do the abbreviated electron configuration. All right, so for the abbreviated electron configuration, we first need to figure out what the noble gas core is. So for 10, right, number 50, go up into the end, we have a krypton core. So I've got a krypton core, noble gas core. And then starting from krypton, right, we'd have the 5s2. All right, so I want to write that down first. We got our 5s2. Then we'd have our 4d fills at 10. That would take us to cadmium, so 4D10. And then past that, indium and tin to finish it out, this would be row 5, 5P1, 5P2. So 10 here would be 5P2. All right, now that is the abbreviated electron configuration. Technically, when I'm looking at just the valence electrons, remember the valence electrons are just those in the highest occupied shell. So I would only take the 5s and the 5p. So the valence electrons here would be the 5s2 and the 5p2. So there's a total of 4 valence electrons. So if I did my group numbers right, if I go back to my periodic table, 10 is in group 4, right? And so that makes sense. There's my 4 valence electrons, 2 plus 2 is 4. So what happens with the D subshell and the F subshell also is if the D subshell becomes full, as it fills, it lowers in energy. And then once it's full, it actually becomes core. So a filled D or a filled F, those electrons become core. So the valence is always those that are in the highest occupied shell, right? Now, if the D subshell is not full, like you have iron or silver or molybdenum or something like that, and the D subshell is not full, then those D electrons are part of the valence, right? And we'll look at that on the next example. But for this, I know sometimes students want to think that, okay, I got my noble gas core, so everything past that is valence. So it's not necessarily true. If the D is full, that acts as core. So it's just the 5s2 and the 5p2. Those are the valence electrons. Those are the electrons in the highest occupied shell. All right, now if I do an abbreviated orbital diagram, okay, so for the orbital diagram, abbreviated, just like the abbreviated electron configuration, we'd have a krypton core. For the S, right, just like we saw with the aluminum, we would draw one box. It's got 2 electrons in it, so 1 up, 1 down. When we get to the D, right, D has 5 orbitals. So there should be 5 boxes for D. So we're going to have 1, 2, 3, 4, 5. All right, and this is my 4D subshell. Each orbital has a max of 2 electrons. And since there's 10 here for 10, 2, 4, 6, 8, 10. There's going to be 2 per box, and they're going to have opposite spins, right? So 1 up, 1 down in each box. All right. And then when I get to my 5p, 1, 2, 3 for P, and we talked about arrow up in the first box. That second electron goes arrow up into the second box. And then if I had 1 more electron here, so going from tin to antimony, 5p3, I'd put 1 up in the third box. So the order of filling is you go up, 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 and then back, down, down, down for a P subshell. All right, now the 2 terms that we really didn't see from intro chem were terms called paramagnetic and diamagnetic. And I talk about this in the Zoom session. I have to say this tripped me up because in my mind, I thought para should mean paired because that seemed intuitive and I wasn't paying close enough attention, and it's not so. Diamagnetic, think di for 2, right? So when you have your orbital diagram, if all of your electrons are paired, then you would say that it is diamagnetic and it doesn't have a strong attraction to a magnetic field. If you have unpaired electrons, then you have paramagnetism and it has more of an attraction for a magnetic field. So when you look at both of these atoms of aluminum and tin, these would both be paramagnetic. Okay, so aluminum, when we do the orbital diagram, we can see it has 1 unpaired electron. When we look at tin, the atom, we can see that it has 2 unpaired electrons. All right, and if it has unpaired electrons, again, it's paramagnetic. All right, now both of these, what we've talked about so far is these are atoms. What happens when we make ions? Okay, because of course that's the next step. So what we were talking about here, like with aluminum, we learned aluminum is always a positive 3 cation. It loses 3 electrons always. We learned this back in intro. We wanted to always remember the 3, 2, 1 diagonal. So aluminum is always a 3. So what three electrons does it lose? Well, like we were talking about, it's not going to take from the core because those are, again, that's the stability switch. You can't take those. I've got 1, 2, 3 electrons here to get rid of or to release. So what happens is that when aluminum loses those 3 electrons to become the aluminum cation, it ends up what's called isoelectronic, iso meaning the same, electron configuration, so isoelectronic. It has the same electron configuration as neon. So if you were asked to do the abbreviated electron configuration for the aluminum plus 3 ion, it would just be neon because the 3s2 and the 3p1, they're gone. We lost those 3 electrons. So aluminum plus 3, that equals the neon structure. And when it comes down to it, the representative elements, for the most part, they want to match the noble gas structure. There's something nice and stable about that with the S2P6. Now, with the type 2 cations and the transition metals, it becomes a little more complicated. The d orbitals, they make things more complicated, which is why my master's was in organic chem, because that's the transition metals, right? That's where I think it's, I don't know, at least that's what I found interesting. But anyway, if you remember 10 was a type 2 cation, meaning it could have 2 or more possible charges. And the first one, stannous, is a positive 2 cation, so 10-2. And the other one, stannic, which is a positive 4 or 10-4. Those are the 2 cations that you have for 10. So the d orbitals make things a little bit harder to predict, right? We said that they do act as core electrons, but they still sort of muddy the water a little bit. So when we're looking at the 10-2 cation, it's lost 2 electrons. What's interesting is always the electrons you add last are the first to go. That seems to make sense, except when there's unfilled D, right? And so that's what we have to talk about when we talk about the exceptions in the next section. All right, so we do 5s2. When we fill the 4D, it acts like core, so we're not going to take those. And then we do the 5p2. The 5p2 is what we're going to lose when we make that 10-2 or stannous cation. So what we would have for stannous is we'd still have that krypton structure core. Then we'd have the 5s2 and the 4d10. So we lost the 5p2. When we look at the 10-4, now what we're going to have is that krypton core still. We're not going to touch those. And even though we fill the 5s before the 4d, remember when the d are filled, it starts to act like core. So we're the +4, we already took away those 2 in the p. The other 2 are going to be in the 5s. So the D, because they're full, they act as core. We're going to take the 5s first. And I think that does make sense, though, in the sense that those are the electrons in the highest occupied shell. So we're going to take those away from the nucleus or from the structure first, right? They're farther away from the nucleus. So what you have with 10-4 is you've lost the P2 and you've lost the S2. So +2 +4 total. So we'd have the krypton core and then we'd have that 4D10. All right, so those are the 2 possible cations for 10. Now I want to do a negative ion just to make sure that we're good here. So let's say we had, I'll just do something kind of simple. Let's say we had fluorine, the atom. So fluorine has a helium core, not much help there, and then a 2s2, 2p5. All right, that's the atom, right? So no charge here yet. So that's for the atom of fluorine. The orbital diagram, we'd have our helium core. Then for the 2s, right, we'd have 1 box, 2 arrows in it, 1 up, 1 down. And then for the 2p, we need 3 boxes always for a p subshell. And again, that order of filling, just to illustrate, you go up and then up and then up and then back down on the left, down and down. All right, so we'd have 2 pairs and a single. So what we can see here is that there is 1 unpaired electron for the fluorine atom. All right, now fluorine, looking at our periodic trends, which we'll get to later, really wants another electron, super bad. So fluorine very easily becomes fluoride. All right, and so with the ion now with -1, instead of having only 9 electrons, it now has 10 electrons. So it's filled that space. And remember, the stability switch clicks on when that happens. So fluoride with 10 electrons now, that matches or is isoelectronic with neon. So a lot of times with the anions, the noble gas thing kind of confuses students because you're like, wait, isn't the noble gas core helium? Yes, when you're looking at the atom, we have a helium core, then 2s2, 2p5. All right, and there's my 7 valence electrons, and fluorine is group 7. But when I look at fluoride, right, instead of having 2 plus 2 plus 5 or 9 electrons, now we have 10. And 10 electrons means it's going to match the structure of neon. So the anion, the negative ion, you're always moving forward. If you're having a cation, you're losing, so you're moving backwards. So nitrogen, oxygen, fluorine ions match a neon structure, right? Sulfur moving forward, gaining 2 electrons would match the argon structure. But aluminum, because it's a metal, it's going back to match a neon structure. All right, so like we talked about, isoelectronic means you have the same electron configuration. So aluminum +3, right, had 13 electrons in the atom, but now only has 10 electrons, so it matches the structure of neon. And we see the same structure with fluoride. All right, those are all isoelectronic. So if we were looking at this, another one would be oxide, right, oxygen -2. Or another one would be magnesium +2, right? All of those are isoelectronic ions. All right, then the last thing to talk about here before we talk about trends is when you make an ion, like gaining electrons, losing electrons, does it become bigger or smaller? All right, and this one I thought was really, I felt like it was pretty intuitive. So let me turn the page here. Okay, so first thing is, actually, let me not go up quite too far. There we go. If I look at the aluminum example again, because we had it on the last page. So with the aluminum atom, I had a neon core and then 3s2 and 3p1. When I'm looking at the aluminum cation, +3, now I've just matched the shape of the neon. So if I go back to that sort of generic structure of the atom. So I've got my nucleus, my first shell, my second shell, and my third shell. In the case of the atom, I have filled the first shell, the second shell, and I've put electrons into the third shell. In the case of the cation, I have emptied out the third shell. So ionic size or radius is the distance from the nucleus to the highest occupied shell. All right, so the atomic size here goes from the nucleus to the third shell. The ionic size only goes from the nucleus to the second shell. So always when you lose electrons, you become smaller. Your distance from the nucleus to the outermost occupied shell decreases. That always made sense. If you're losing electrons, you're going to get smaller. So again, like the way to visualize it is in the aluminum atom, I've got the first shell full, second shell full, and now I've gone into the third shell with an S2P1. But when I make that aluminum cation, that S2P1 is gone. We've gotten rid of those. And so now what's left is just going the 0 and the second, or sorry, the 1 in the second shell. So we went from going nucleus to third shell in the case of the atom to just nucleus to the second shell. So the cation is always smaller. So the cation is always smaller than the atom. But you have to compare apples with apples. Like if you're looking at aluminum, you have to be comparing it with aluminum. It's not like you're going to compare sodium ion with magnesium atom or something like that. Like you're going to compare the two elements that are the same, just looking at the atom versus the ion. Then the opposite would be true. So like, let's say we had the fluorine atom, which was the helium core 2s2, 2p5. And then let's compare it to the fluoride, which now matches the shape of the neon or the configuration of neon. Now, in both of these cases, we got our nucleus, first shell, second shell. So Both of these only have electrons in the first two shells. So you might say, well, aren't they basically the same size? Here's what the difference is. In the atom, I've got 9 positive particles in the nucleus, atomic number 9, and I have 9 electrons. In the ion, I still have the 9 positive particles in the nucleus, but now I have 10 electrons. And the idea is that positive particles in the nucleus attract the negative particles, the electrons. So if I add electrons here, the positive center isn't going to do as good of a job as attracting those electrons closer to the nucleus. So it turns out, and that, again, it kind of easy to remember, when you lose electrons, you become smaller. When you gain electrons, you're going to become larger. All right, now you typically not as much of a difference as when you do the cation and you actually empty out an entire shell, but it will make it larger. So your anion is always larger than the atom. So your fluoride is larger than your fluorine. All right, so that's ionic size. Okay, so then the last thing in the chapter are the periodic trends. And for the periodic trends, we learned 3 in intro chem. This might seem familiar. We have atomic radius, ionization energy, electronegativity, which we're going to need a lot in the next chapter. And then there's metallic character. That's the new one. Before I do that, though, I forgot. I wrote myself a note. I'm glad I did. There are, with electron configurations, there are 3, technically 4, exceptions that we want to remember. And of course, they're transition metals. So we've got chromium and molybdenum, and then we've got copper and silver. So let's look at chromium. All right, so chromium, all right, number 24, the electron configuration, the core, I've got an argon core, and then I'd have 4s2 and then 3d4, right? 1, 2, 3, 4. So for krypton, we have an argon core, 4s2, 3d4. So part of the reason why I loved learning about the transition elements is that when you look at this on an energy diagram, when the subshells and the orbitals are not full, so this is increasing energy, your 4s is about here, and then 1, 2, 3, 4, 5, there's your 3d. So the D is just slightly higher in energy, which is why the electron prefers the 4s first. And then what we were talking about, this is a pretty small separation between the two. And as the D starts to fill, it actually drops in energy. So what ends up happening is you have your 4s2 and then your 3d4 for chromium. What ends up happening here is these 2 electrons that are paired really don't like being paired, right? They lose energy by being paired. And energetically, it's actually more beneficial for that electron to say, you know what, I'm out of here. I'm going to take my own seat, because the energy that it loses by jumping up to that 3D is less than the energy it loses by pairing. So chromium actually becomes an argon core, 4s1, 3d5. All right, so it's one of the exceptions that we want to remember. Molybdenum, which is right underneath chromium, so it makes sense that it's going to be exactly the same. The only thing that's different is instead of an argon core, it has a krypton core. So it's got a krypton core. Instead of 4s2, it's 5s2, and then 4d4. But again, the exception here is it becomes the krypton core, 5s1, 4d5. All right, so that's the first couple of glitches that we have with these electron configurations. And we didn't learn those in intro. So that's the first 2. So chromium and molybdenum, you'll remember this. They're in the same family. We expect tungsten to probably behave similarly, right? Instead of an S2D4, again, the idea is let me not have this reduction in energy by repulsion. Let me take less of a reduction in energy, but still a reduction by just moving up to that D. So the electron takes its own spot, and energetically that's better. Even though it's moving up in energy, it's not losing energy from repulsion. So that's the first glitch. The copper and the silver is the next one. All right, so on my next page, copper, and you can probably guess where this is going. Copper has an argon core, 4s2, 3d9. All right, now this one, when you have your energy scale, right, here's your 4s, 1, 2, 3, 4, 5. There's your 3d. And we start out paired, pair, 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 and then a single at the end. But remember here, what happens is that as those d orbitals start to fill, they actually are going to drop in energy. So we don't have exactly the same as we did up here, where the energy jump to go up to the 3D is less than the energy lost from repulsion. This actually, what happens is the D and the S, they kind of switch places in energy. So the D sublevel, that energy level, right, that energy, that actually starts to drop. And it turns out that the electron, it's really close though, prefers to go as a 3D10. But that electron kind of bounces around a lot. And we know that because copper is typically a +1 or a +2 charge, right, for the cation charge. So they say that copper, the exception is 4s1, 3d10. But truly, both of those are going to be possible. And the electron bounces around a lot, again, because we know copper has two possible oxidation states or charges. It's either a copper 1 or a copper 2. And it makes sense. If we're looking at the electron being in an S1D10, it's going to be a +1 charge. If it's an S2D9, it's going to be a +2 charge. So copper, a little bit trickier, right? But this is what they say happens with copper, to just remember it's an S1D10. Silver, I think, is more of a hard and fast rule that it is an S1D10, because if we remember, silver as a cation is always a +1, right? So that makes sense then that it has a krypton core and then it is a 5s1, 4d10. It's always +1. So it always just loses that 5s. So I think in the case of silver, that exception is always true. I think copper though, there's some variability there. But anyway, those are the exceptions. So chromium and molybdenum, and then the other two that are in the same column, we've got copper and silver. All right. Then for the trends. Okay, so the trends on the periodic table, the first one we have is atomic radius or atomic size. All right, and I like mnemonics that help me remember things. So what we're looking at here is the distance from the nucleus to the highest occupied shell. All right, so when we do this, we're just looking at qualitative trends. And the first one within a family is usually very intuitive. If I look at nitrogen, phosphorus, arsenic, antimony, bismuth, it makes sense that as I go down a family, that size is getting much larger. I'm adding shells, right? Nitrogen only 2 shells, phosphorus 3, arsenic 4. So we know that as we go down a family, atomic radius increases. The side-to-side trend was trickier for me because when we were talking about ionic radius and what happens with size, we learned that when you make an ion and you gain electrons, you're going to become bigger. And I remember getting confused by this, thinking, okay, well, if I go across the periodic table, I'm gaining electrons, I should be getting bigger. It's not the case. So this one I remember tripped me up. So what happens here is I've got lithium with 3 electrons, 3 protons, second shell. And then I've got fluorine, 9 protons, 9 electrons, also second shell. So everything in row 2 has 2 occupied shells. So their radius is probably fairly similar. But what happens is as I go across the periodic table to the right, I'm adding positive charge to the center. And those positive particles attract the negative electrons. So what you end up happening, like what ends up happening is that second shell, as I go across the periodic table to the right, it starts to contract a little bit, right? It's being pulled in because my positive charge in the nucleus is going up. So what is kind of strange is that elements on the left is, again, as long as we're in the same row, elements on the left are actually larger. And I think I remember on my test getting something like cesium and lead and being like, there's no way cesium's bigger, right? Because if you look at your electron count, we got 55 and 82. There's no way. You can Google it. There's a way, apparently. So the trend is true. If you go to the left, right, your atomic radius is increasing. So the way to remember this nice and easy, atomic radius, also called atomic size, but I like atomic radius better, is I remember AR, atomic radius, points to FR. So when I look at my periodic table, if I go all the way to the left and down, there's francium. So made it easy to remember, AR goes to FR. Okay, the other two from intro we had were electronegativity or electron affinity and ionization energy. And I'm going to put these side by side because they look almost identical. So electronegativity is the measure of an atom's desire to gain an electron. All right, so what we know is as we go across the periodic table to the right from metal to nonmetal, that desire to gain obviously goes up because metals never gain electrons, but nonmetals always do. So we know electronegativity increases to the right. In terms of the family trend, the smaller the atom is, the more of an attractive force it can have. Because if you think about it, it's offering a seat to an electron that's going to come in. The closer that electron can get to the nucleus, the better the offer, right? So as that atomic size is getting smaller, the more electronegative that element can be. Ionization energy is the energy required to remove an electron. So again, definitely increasing as that size gets smaller because the electron is closer to the nucleus, it's more difficult to remove it. And then also as that energy shell starts to fill, right, it's going to become more and more difficult to remove the electron. Metals lose electrons really easily, non-metals not at all. So we know both of those trends look almost identical. Here's the exception. Electronegativity is the desire to gain an electron. Noble gases have none of that. So take out your noble gas column and up and to the right, fluorine is our most electronegative element. Now, ionization energy is the energy required to remove an electron. And you can do that with a noble gas, but it's not going to be pretty, right? So I always remembered ionization energy, IE, points to HE. And electronegativity looks almost exactly the same. We just stop a column short. We go to fluorine. All right. Then the last one, this one we didn't have from intro, was metallic character. And actually, I'm going to take that back. I'm going to go up here. You'll see why. Metallic character, I think, is also sort of easy to guess. What we know when we look at our periodic table is we have nonmetals on the right, we have metals on the left. So we understand metallic character should be increasing as we go to the left. So metallic character increasing to the left. If I look at a family, carbon, nonmetal, silicon, germanium, metalloid, tin, and lead, metal. So we're thinking metallic character increases as we go down, and that's true. So metallic character and atomic radius, those look the same, right? So again, that would point to francium. So the two of the trends go together. The other two trends are also together. They're just the exact opposite. So atomic radius, metallic character both increase to the left and down. Electronegativity and ionization energy both increase up and to the right. Okay. So the types of questions you'll see on the practice quiz is I'll give you 3 elements or 4 or whatever, and I'll say, okay, of the 3, which one has the highest electronegativity? Which one has the highest ionization energy? Which one has the lowest, right? So you're just using those trends to qualitatively decide which one's most electronegative, which one's least. Most electronegative is closest to fluorine. Least electronegative is the one farthest away, right? So that's what you want to be able to do for your periodic trends. In terms of chapter 9, that's really it. We learned electron configurations, how to figure out valence versus core electrons, looking at orbital diagrams. We did the exceptions for the electron configurations with the chromium and molybdenum and then copper and silver. Then we looked at, okay, if an ion is formed, what electrons are coming and going. Paramagnetic, again, means that you have unpaired electrons. Diamagnetic means everything is paired, which would be the case with like a noble gas, right? Everything's paired. Then we looked at our periodic table trends, right? The 2 and the 2. So in terms of this chapter, that's pretty much it. I think I did my homework. I just haven't posted it yet. I forgot to bring it to scan. So I will do that hopefully tomorrow, but Thursday at the latest. But anyway, I think this chapter will be sort of a nice change from the past couple that we've had. So I'm going to stop there for now.